Welcome to the fourth BP-ICAM webinar of 2019. Over the next hour, Professor Costas Soutis from the University of Manchester will discuss aerospace applications of modern composite systems. So Professor Soutis' presentation will last for around 45 minutes. He'll be able to answer any questions you might have at the end of the talk, so please do use your comments box in the bottom right-hand corner of your screen to pose any questions as we go along or at the end of the session. Professor Soutis is the Director of the Aerospace Research Institute and the Director of the Northwest Composite Centre here at the University of Manchester. Prior to this, he held professorial positions at both the Imperial College London and the University of Sheffield. He's a Fellow of the Royal Academy of Engineering and a leading authority in mechanics and failure of composite materials. He's co-authored more than 400 articles, and some 40 PhD students have successfully completed their studies under his supervision and guidance. So without further ado, I'm delighted to hand over to this afternoon's speaker, Professor Costas Soutis.
Thank you so much, Claire, for the kind introduction. And I would like to thank also BP-ICAM for the invitation to come and talk today about aerospace composites with built-in functionality. Of course, I would like to say good morning to Illinois if they have connected with us, and good afternoon to the Europeans and to the people in the UK. Hello from Manchester, home of first industrial revolution. I don't know who is now the
Can you hear us a bit better now? Great. Hopefully everyone can hear us. If you can't hear us with this now, just let us know in the message box.
Okay, I hope that you can hear us better. Okay, I was talking about the home of first industrial revolution, Manchester. And I asked the question, what is the home of the fourth industrial revolution? Anyway, we'll find out. A few things about Manchester. We have a big activity on materials research, from lightweight alloys for planes, trains, ships, and cars to high temperature materials for jet engines and power generation, to electronic ceramics and polymers, to biomedical materials for implants and tissue engineering, to engineered smart textiles and composites. So today the talk is going to focus on composites at Manchester, and composites with built-in functionality. For those that they're not familiar with composites, I have to say a few things. Composites bring the properties of two or more materials together. So any two materials, metals, ceramics, polymers, elastomers, glasses, could be combined to make a composite. They might be mixed in many geometries, particles, chopped fibers, woven, unidirectional, and laminate composites where you design and you build layer by layer, and you create a system with a property profile which is not offered by any monolithic material. So for instance, in mechanical design, it is often to improve the stiffness to weight ratio or strength to weight ratio, or improve toughness, while in thermomechanical design, it is to reduce thermal expansion, or to maximize heat transfer, or to minimize thermal distortion. Of course, you can always design and tailor the electrical conductivity of those materials systems. So layer by layer material engineering, we start with carbon fiber. It can be in a unidirectional pre-preg format, or it can be as a woven fabric, which is mixed with resin. And then we can build multi-layer constructions in order to satisfy certain criteria, as we said, based on stiffness, strength, toughness, thermal or electrical properties. But what are the benefits? Most of us are familiar with composites, and the main reason for, especially in aerospace, is weight saving when we compare to traditional aluminum alloys. They provide us high strength and stiffness. We can tailor directional mechanical properties. We can create complex shapes and contours. But the most important aspect also, it enables you to reduce part count over metallic equivalent. You can reduce machining effort. They do not corrode and they behave well in aggressive environments. And they can provide excellent fatigue resistance. I mean, the composites people, of course, they claim that composites do not fatigue. But I'm sure that everybody fatigues, so composite systems also fatigue. And we'll talk about that later on. But the other big benefit that they offer us is the potential for embedded functionality in terms of sensing, self-healing, and a few other concepts that we'll try to cover in this presentation. Where are they used? In aerospace extensively, energy, marine, construction, transportation. But then if we look at commercial applications, we're going to see that these material systems are relatively new systems. And the first commercial application appeared in 1983 when Dunlop produced the first carbon fiber tennis racket. And a few years later, in 1995, McLaren, they built the carbon fiber composite frame, the Formula One car. I want you to remember those dates, 1983 and 1995. I'll ask you questions later on. If we look at aircraft applications, fabrication of aircraft, modern aircraft, composites do enable us to innovate. And here we can see the winglet of the Airbus A350. It's about 7 meters long, and it's made entirely out of carbon fiber. It could be made out of metallics, but it could be too heavy. Here's another example of complexity. This is the complex inlet duct of the F-35, manufactured by ATP, advanced tape placement. And we spoke earlier about fatigue, and this is a demonstration where we compare the size of the window offered to us by the Boeing 787 and the Airbus A380, which is mainly a metallic airframe. And you can see the composite airframe of the 787 enables the engineer to more comfortably provide us with a better view of the clouds. So the 787 is the industry's first composite wide-body jet. And that's an example where composites, they don't fatigue as much as metallics. But of course, as we said, everything fatigues. And here we can see how damage evolves in a composite multi-layered construction. Here we have a Cibble 090 laminate, and we can see how damage initiates in the form of matrix cracking in the 90-degree layer. At the tip of the crack, you develop now a three-dimensional stress field where maybe it doesn't have enough energy to break the neighboring plies, the fibers in the zero ply, but they're high enough to introduce delamination, separation of neighboring plies. And if that laminate is loaded under biaxial loading, then you're going to see that matrix cracking or splitting starts to propagate in the zero layer. And this type of resin microcracking can also occur not only due to static loading or fatigue loading, but also to thermal loading, or high-growth thermomechanical combination of loading, something that an aircraft experiences when in service. So the damage mechanisms are under tension. They are in the form of matrix cracking that causes degradation of the overall stiffness properties of the laminate. And that triggers development of other damage modes, delaminations and fiber breakage. And our community then puts an effort to develop analytical models that can describe what is the effect of all these damage mechanisms on the performance of the composite structure. Something happened here to some of these images, and some distortion took place. Maybe they have fatigued as well. And then on this one, we look at this internal damage, which is non-visible damage. And in this particular case, we have a multi-layered carbon fiber plate with an open hole, which has been loaded to 85% of its ultimate static compressive strength, and there is no visible damage. So we're not aware if there is any damage inside this construction. And the only way we can observe this one is by using X-ray CT, computed tomography, where we can see some actual cracks growing by the edge of the hole, some off-axis matrix cracking in the plus and minus 45 layers, and extensive delamination between those plies. But of course, that image there has failed to identify on the left-hand side of the hole, under those delaminations, there is a critical damage mode in the form of fiber microbuckling that we cannot see and we have failed to detect. Here we can see on the left-hand side an optical micrograph where there's a thin crack growing across the width of the laminate from the edge of the hole. And it looks like a fatigue crack in metals under tension. But this one is not under tension, but it's under compressive loading. And if we go to SEM scan electron microscope, we're going to see that that crack is in the form of fiber microbuckling in the zero plies, that they carry the actual loading. And those microbuckles, obviously, it's a fiber instability failure mode. When it reaches a critical strain, they break and the crack grows in an unstable manner, causing catastrophic failure. So here we can see the schematic and the SCM micrograph that shows the fiber microbuckling of the zero plies. And that reduces the strength, the compressive strength, by 30 to 40% when it's compared to the equivalent tensile strength for the same laminate. And there is effort to develop analytical models that will enable us to estimate the critical stress in the zero layer that is going to introduce that fiber instability, taking into account the initial fiber waviness, the fiber volume fraction, the properties of the fiber in the matrix, the entire non-linear response of the resin, and also the interlaminar shear stresses that they develop between neighboring plies, that they can also introduce additional instability in the zero layers. Again, there something happened to the equation. Lots of question marks there. Maybe later on we have to circulate the PDF file. And the effort now is focusing on how we can identify those critical damage modes that they take place inside the component non-destructively. And here we can see an electromagnetic sensor, which is electromagnetically coupled spiral inductor. It's a homemade, it's a very low cost homemade that we developed here at the University of Manchester, and it enables us to identify non-destructively delaminations that can happen not only in UD pre-preg laminates, but also in woven fabrics. But much more work is required. And we have some new arrivals today from Napoli that is going to put effort in that struggle to identify suitable methods of non-destructive evaluation of composites. So we spoke about the non-visual damage, not visible damage, but what about the damage which is we get other, say, low velocity impact or a bird strike impact? Here, of course, the task is not so much to identify the damage, because we can see it without any sophisticated method, without an X-ray or X-ray CT or electromagnetic sensors. But the task here, the challenge, is how to fix it, how to repair it. How to repair it without actually causing additional damage during the process. So then the community put effort trying to identify ways of making composites more resistant to damage. Of course, eventually they will get damaged, damage will occur, but how you can delay it? And one way that composites offer us is hybrid composite laminates. Of course, the concept is not new. We can see here Prince Achilles with his shield, which is a composite laminated structure similar in design to those applied in modern aircraft construction, like the Airbus A380, where the upper part of the body is made out of fiber metal laminates, glare. So if we look at the shield, it consists of two outer layers of bronze, two inner laminae of tin, and one central lamina of pure gold. I don't know if we use gold today to build our aircraft, but after all, Achilles was a prince, so he could afford to have a bit of gold there. But if you look at the construction, it's been optimized for strength and stiffness, while the pure gold, the softer material, provides a bit of toughness. So the spear cannot break the shield in a brittle manner, and at the same time cannot penetrate. So based on this principle, we can see the carbon fiber composite on its own under a blast event in a pressurized aircraft cabin, where we can see a big hole is created, and we don't want that. We don't mind to get damaged, but we do mind to get perforation. And if we compare that with a fiber metal laminate under a high velocity impact, we're going to see that the aluminum layer in this case has absorbed all the energy from the blast. Yes, we have inner damage in the other layers, but we managed to avoid perforation. Another way of achieving toughness and preventing early damage in the form of matrix cracking and delamination is if we can mix different fibers together. And in this example, for instance, we have glass fibers that they provide the strength and the stiffness in our construction, mixed with polypropylene fibers that they provide this additional toughness in our composite system. They make it harder, they can sustain higher strains, they can make it harder for the composite to get damaged. Eventually, it will get damaged, and under an impact event, you will have the same the same damage modes and the matrix cracking and delamination and so on and so forth. But now the composite enables you actually, if you hit the composite, you can melt those polypropylene fibers. They can fill those cracks, matrix cracks and delaminations. And then when you look at the tensile strength after impact, we have recovered quite a lot of the original strength of the laminate. The third option that we have with composites in the effort to improve damage resistance and make them more damage tolerant. Of course, damage tolerance, it means that you can still perform your task in the presence of damage. And the third dimensional reinforcement, 3D woven fabrics, they provide us with the ability to delay or prevent those delaminations. And under an impact event, we can see and we can compare the two-dimensional fabric under the same impact conditions with a three-dimensional one where all the delaminations have been prevented. Extensive delamination develops in the two-dimensional material, but not in the 3D. Of course, there is very little you can do about the broken fibers. In both cases, we have broken fibers, but we don't have the same amount of delamination as in the two-dimensional fabric. And then, if we look at the tensile behavior of the 3D woven architecture before the damage, before the impact event, and after the damage, which is the red line in our graph, we can see actually the notch strength of this 3D woven architecture is almost the same, very similar to the undamaged configuration. So here, what we can see that we have removed material from our plate in the form of damage, and that damage, it doesn't affect the tensile behavior. It affects very little the stiffness, and it doesn't affect the ultimate strength and its ductility. So some progress there has been made. So we spoke about this layer by layer material engineering, where we have the carbon fibers or the woven fabrics mixed with resin, and we try to find ways of making our composite construction more damage resistant, more damage tolerant. And the final way of doing that, since we come from Manchester, we're going to introduce a magic ingredient in the form of graphene. So instead of using the 3D fiber architecture or the hybridization, we try to modify the resin and make the resin tougher with graphene particles. I'm sure many of you are familiar with graphene and how graphene can improve composite performance, how they can make our composite more damage tolerant. But I think the area actually where graphene can give us many advantages in our composite fabrication and construction is electrical functionality and high temperature tolerance and electrical conductivity. But before doing that, let's see what is graphene. It's a multifunctional nanomaterial additive for polymers and composites. It's a two-dimensional material, one atom thick, with some superb properties. We claim that it's the thinnest, the strongest, the stiffest, the most stretchable. There's a long list of good things that graphene can offer us. And if we look at the stiffness, it's 1 terapascal with a strength of 130 gigapascals. And of course, always the question is how you can measure those properties, how you can achieve those properties. And here we can see a graphene platelet where we test it with the atomic focus microscope with a nanosensor at its tip, and we derive the stress strain response and measuring the Young's modulus of over 1 terapascal with a strength of 130 gigapascals. But of course, the question is, in order to achieve those properties, your graphene has to be very pure. There are many derivatives. It can be graphite, can be reduced graphene oxide, or graphite oxide. And those other substances might not have the same performance as the graphene that you were supposed to use in the first place. And then the other big challenge is how you can manufacture graphene, how you can make graphene. There are, of course, the two approaches, the top-down and bottom-up. Top-down, production by removing elements from a large starting material, or the bottom-up approach, where you assemble of a nanostructure from smaller elements. So you can use the electrochemical exfoliation technique, or the chemical vapor deposition. And of course, both methods are supposed to give you the same material with the same performance. But we know very well that during the fabrication process, many things can happen, and the purity and the performance of the final material might not be the same. And if we look at the electrical conductivity of this graphene reinforced polycarbonate, we can see its conductivity increases by 12 orders of magnitude, where you have only 1% by volume graphene platelets. Again, there you can see that the performance depends very much if you have the emulsion mixing or solution mixing of your graphene. So straight away there, the way you fabricate it, the way you mix it, has an impact on the performance of your composite. We spoke earlier about the healing potential of the hybrid composites, where we had the plate under impact, where we managed by heating to repair the resin cracks and the delaminations. And of course, if we have graphene in our resin, then graphene will increase dramatically the thermal conductivity of the epoxy resin and speed up the healing process. And ideally, when you build material systems, you would like to build the material from scratch, atom by atom engineering. And that will enable you to build in functionality in your multi-layered system during the material production. And somewhere there, you might have a layer that can be your sensor, a few layers that they can be your transistor, and it interconnects the whole system. And further down, a few layers that they can act and provide the mechanical reinforcement, give you the strength, give you the stiffness. And somewhere there, you could have a solar cell that is going to generate the energy in order to run all this heterostructure and perform in a way that metallic materials cannot do. And once you have this kind of material system, then of course you can have applications in high frequency electronics, sensors, flexible electronics, energy, composites and membranes. You can have a graphene antenna that could give us wireless terabit uploads in 1 second. Whew. Graphene filter covered in tiny holes, just big enough to let water through, but small enough to keep salt out, making salt water safe for consumption. Graphene supercapacitors that can fly the aerospace mini UAV forever, actually, making batteries obsolete. And then we go back to those composite airframes like the Airbus A350 and the Boeing 787. Those structures, those carbon fiber composite aircrafts, are currently covered with a copper mesh for protection against lightning strike. Which, of course, then, by adding this additional load, you take away the advantages that carbon fiber systems, they offer us in the first place. And the question is, could a conductive graphene modified epoxy matrix provide protection? Can we provide that protection during the spraying, the paint, when we paint the aircraft, and we have the graphene nanoplatelets that they make the whole thing electrically conductive? What was the year that the first carbon fiber racket appeared by Dunlop? 83? Or was it 85? 83, it was 1983. So it took us several years before the head managed to produce the first graphene tennis racket in 2014. I don't know how much graphene you can find in there, but that's the claim. There is a graphene reinforced tennis racket. And then on the top right, we can see, who is that guy driving the Lotus? That's a graphene reinforced Lotus. That's Prince William. Prince William, who visited the University of Manchester a few years ago, or a couple of years ago, maybe less. And we showed him the graphene reinforced carbon fiber Lotus car. And then you have the smart phone at the bottom right corner, where the idea there again is to replace that brittle glass screen with plastic touch screens that use graphene as their conductor. And it doesn't matter how many times you drop your smartphone, you will never see that you have smashed the screen. So it might be graphene composites the future. Haha! And here what can we see? We can see master graduates wearing their gown, graphene enhanced smart clothing. It might happen. I don't know what kind of advantages that is going to give you. Maybe it might give you warm. I don't know. We have to test it. Smart clothing. It is happening because it can measure your blood pressure. Of course, we've seen composites used extensively by the aircraft industry, but the area now where composites are used extensively is the automotive. And here we have moved straight away. We have moved from the low production from the cottage industry of aerospace, which is a niche market, to mass production where they build millions of cars every year. And many of those cars and car manufacturers, probably they're not waiting for Professor Soutis to develop those mathematical models to successfully predict behavior. They have already moved into building their cars, like on the left-hand side there is Ford. So all the frame that supports the engine is made out of carbon fiber. Top right is the Toyota Corolla. And the bottom right, do we recognize that car? No? Josh? No, that's a Porsche. So you can see the entire car is built out of carbon fiber. And here, of course, there is a lot of automation. And here people talk about Industry 4.0, or the fourth industrial revolution, where all things are internet connected. And that Industry 4.0 schematic up there, that's the skyline of Manchester, and it's the view from my office. And of course, the car manufacturers, as they're moving away from the internal combustion engine, and they try to reduce the weight of their frame, because batteries, unfortunately, they still remain very heavy. The only way to reduce the weight is to reduce the weight of the frame. So if they save 10% mass saving, 10% mass saving, it will give them 6 to 7% fuel improvement, which is a big thing. But of course, when we try to introduce graphene into composites or any other application, there are barriers and challenges. We spoke already that in order to achieve those super properties, you need to achieve high quality of graphene. You need to develop effective and reliable processing techniques that will enable you to disperse, to align, to deposit, to functionalize, to integrate into your composite system, material system. Then you have to think about scalability and affordability. There are issues with nomenclature. We have to put effort on standards, and still we have health and safety uncertainties. But above all, like all carbons, manufacturing route determines properties and cost. And when we look at today's composite challenges, there is need to increase supply of raw materials, reduce materials costs, reduce finished part costs, processing costs, and we need to increase speed and volume of manufacture. And this is where then Industry 4.0 gives us the opportunity to achieve that. Machining, drilling, assembly, joining, and repair, they remain big issues. But above all, how to design the composite strengths without treating that as a monolithic aluminum material. And as you can see, processing makes 60 to 70% of the total part cost. So we have to put effort on those methods, processing methods. And NDT and SHM of composite structures, how you can identify with confidence all that damage that takes place internally, and it's very difficult to see. And then, of course, when you try to model, again, the metals people, the metals community, they have well-established failure criteria. In composites, still we don't have universally acceptable failure criteria. And then again, you have many questions. Are we going to model at the nano level, the molecular level, the micro level, or are we going to smear out all the fibers and all the layers and do structural mechanics at the macro level? But then we're going to miss out all those damage mechanisms that they take place and the affects the performance. And then in our analysis, numerical analysis, we have to take into account also the manufacturing process. Because we've seen that the manufacturing process introduces fabrication defects that we need to take into account in our analysis when we try to predict the strength, the stiffness, the fatigue life of the composite. So many challenges. I would like to stop there now. I would like to thank you all, the guys from Illinois, the guys from Europe, the guys from the UK,